Welcome to the session on Azure SQL Database Serverless. My name's Morgan Oslake. I'm a program manager on the Microsoft Azure Data Platform team. I'd like to begin this session by first reviewing what serverless is in SQLDB, and then move on into a discussion about when and how to use it in order to best price and performance optimize your database workloads. And throughout the session, touch on various aspects of serverless support for hyperscale that was recently introduced. Now, when customers begin their onboarding journey into Azure SQL PaaS, one of the first decisions to be made is choice and deployment model. Managed instances are ideally suited for lift and shift scenarios due to their very high degree of compatibility with on-premise SQL Server implementations. Elastic pools in Azure SQL Database are ideally suited for multi-database deployments. So for example, SaaS ISV applications that may have as many as tens, hundreds, or even thousands of databases. And then finally, there's the single database deployment model option, which provides the greatest degree of management simplicity, is ideally suited for cloud-borne applications, and is currently where serverless is supported. So before getting into some details of serverless, it's useful to first step back and consider some of the challenges facing customers when price and performance optimizing their workloads. So consider a typical scenario of an IoT application with a centrally managed database that receives rainfall data from thousands of geo-distributed weather stations. And suppose the same database also exposes endpoints that clients can connect to in order to run analytics queries. It's easy to imagine that when the weather is relatively calm, that usage on the database is relatively low, but that say when a storm system passes through, the usage on the database can increase suddenly and to rather high levels of compute. So in a sense, there's a correlation between storm activity and database usage. The key point to emphasize in this example is that the workload demand on this database is unpredictable, both in terms of the amplitude and timing. So this presents DevOps challenges for how best to right-size the compute for your workload in order to achieve your price and performance goals. One option is to provision an amount of compute that can accommodate peak workload demand. But given this usage profile where there are bursts in activity followed by periods of relatively low idle usage, this can lead to an accumulation of wasted resources and ultimately higher costs. On the other hand, you could decide to provision an amount of compute corresponding to the average usage over time, but then because there's insufficient capacity during these bursting episodes, the application can suffer from poor performance. Now, if the database is already in the cloud, you can take advantage of compute elasticity and consider building your own custom rescaling automation. But this involves monitoring and workflow orchestration of rescaling, which of course adds to development costs and operational complexity. So that's just the kind of scenario that serverless is intended to address. Serverless in SQLDB essentially provides two key scaling capabilities. The first is automatic scaling of compute over a configurable range that's indexed by a minimum and maximum number of cores corresponding to a range in memory as well. And whatever the workload demand of the database happens to be from one point in time to the next, serverless is automatically right-sizing itself and providing just the right amount of CPU and memory resources. The second key scaling capability in serverless is automatic pausing and resuming. So in this case, after a configurable period of time called the auto pause delay, where the database has been inactive, the serverless will take the liberty to pause the database, pass those additional cost savings back to the customer, and then automatically resume the database once activity returns. Billing for serverless is fundamentally based on the amount of compute used on a per second basis, both in terms of vCores and memory consumption. So in this chart on the right, we have an example of a serverless database that's configured with a min of 1 core, a max of 8 cores, and it's showing its usage in compute over a 24-hour period by this orange jagged line. And while that usage is between the min and max vCores, it's being billed precisely for that usage. Later, over this 24-hour period, when usage drops below 1 core, that 1 core continues to be billed until the database is idle for this 1 hour period based on the auto pause delay that was configured by the customer. And after that elapses, that time elapses, the database is automatically paused. And because we terminate the underlying compute for paused databases, we pass those cost savings back along to the customer, at which point only storage is billed. Now, outside of these scaling benefits and pay for compute usage benefits, serverless provides all of the same manageability benefits that you would expect in Azure SQL PaaS. So high availability is built in. Backups and service updates are performed automatically. There's machine learning running in the background, looking for opportunities to provide you with security and various performance-related optimizations. So what are the kind of usage patterns that are ideally suited for serverless? Typically, databases with intermittent and perhaps unpredictable usage such that the compute utilization on average over time is relatively low, serverless tends to be a good fit for pricing reasons alone. If the database perhaps is already in the cloud and being frequently rescaled in provision compute, then consideration of serverless is natural. Serverless tends to provide much faster scaling, much more robust scaling that then can be achieved in the provision compute tier, where customers can perform their own rescaling operations. And then finally, if the database is brand new, such that its compute sizing requirements are somewhat unknown, the database doesn't have any usage history, then serverless can often be a good starting point. And if for whatever reason it later turns out that serverless isn't a good fit, say for pricing or performance related reasons, the database can easily be moved into the provision compute tier. So not all usage patterns are ideal for serverless. There are certain anti-patterns to consider. So if the usage is more regular, perhaps somewhat predictable, and has a higher average compute utilization over time, then provision compute tends to be a better fit for pricing reasons alone. It's also important to understand that because serverless at its heart is a auto-scaling solution, when databases begin to scale up, they may suffer briefly from some performance impact due to the period of time required for the compute to warm up again. And then finally, if you have multiple databases that can be consolidated into the same elastic pool, then elastic pools tend to provide better price optimization. This is really largely because elastic pools provide better compression of usage per unit of compute. So until recently, serverless was only supported in the general purpose tier, but more recently, support in hyperscale has been introduced. So you can think of serverless and hyperscale coming together to provide a single database solution. In hyperscale, there's a primary replica that serves as the compute endpoint for both read and write workload. And then unique to hyperscale is the option for customers to configure whatever number of HA replicas are appropriate to achieve their high availability goals. And then finally, in hyperscale, customers can horizontally scale out up to 30 name replicas for read scale. And so if you overlay serverless support on top of this picture, you have a scenario where each replica instance is able to independently automatically scale up to 40 cores and be billed just for the amount of compute that it's actually using. Now, outside of these compute-related benefits and high availability-related benefits, in terms of storage, serverless databases and hyperscale can automatically scale up to 100 terabytes, which is significantly higher than the 4 terabyte limit in the general purpose tier. So another facet that makes hyperscale unique relative to the general purpose tier is its layered caching hierarchy. And because of that, it's able to offer superior I/O performance. So for example, I/O throughput in hyperscale can scale all the way up to 100 megabytes per second, independent of whatever the compute demands happen to be. In terms of latency, because of this caching hierarchy, hyperscale IOs tend to range somewhere in the neighborhood of 1 to 5 milliseconds to complete, whereas in the general purpose tier, those IO latencies are about twice as long. And then finally, because backups in hyperscale rely on taking snapshots, restoring a database of any size, even up to 100 terabytes, completes independent of whatever that size happens to be in just a matter of minutes. Onboarding into serverless is relatively straightforward. So here I'm showing up PowerShell commandlet for creating a new database, and I've highlighted the parameters in yellow that are unique to serverless. So the compute model needs to be specified as serverless. In this example, the min number of cores is 0.5, the max number of cores set is 4, and the auto pause delay is set to 60 minutes. Moving existing databases, say in the provision compute tier, into serverless is equally straightforward. Essentially the same API signature, but it's also worth pointing out that moving into serverless doesn't require any kind of application rewrite. So there's a very high degree of mobility in terms of moving databases either into serverless or out of serverless back into provision compute. So with that, I'd like to first demonstrate onboarding. Here I'm showing the Azure portal. I've pre-created a server called LS2. And what I'd like to do is create a new serverless hyperscale database. So let me begin by clicking this button called Plus Create Database. This will bring up a page in the workflow that's largely pre-filled with database metadata. I just need to provide the database name. Let's call it MyDB. And then rather than accepting the configuration defaults, let me click Configure Database so that I can choose serverless either in the general purpose tier or in hyperscale. Once I've made that service tier selection, I identify the server or the compute tier rather as serverless. And now I'm able to specify the maximum number of cores that this database will automatically scale to, up to 40 cores. And I can also configure the minimum number of cores that the service will never scale below. So you can think of the max vCore setting as providing a way for customers to cap their maximum compute bill. And you can think of the min vCore choice as providing essentially a lower bound in terms of the kind of performance that this database will experience. Automatic pausing and resuming in hyperscale isn't yet supported, but it's something that we're actively working on. And then finally, I can specify HA replicas all the way up to 4. And whatever my min and max vCore choices were above for the primary replica automatically get applied to each of the HA replicas as well. And there's a similar experience to this for configuring serverless for named replicas. Now, once I'm satisfied with my choices here, I can click apply, and just within a matter of several seconds or a few minutes, the database is ready to run. So how does scaling work in serverless? Here I'm showing an example of a serverless database that's been configured with a min of 2 cores and a max of 16 cores, corresponding to a range in memory from 6 gigs to 48 gigs. And suppose at one point in time, my database is performing a select star, which involves a table scan, and so will perform a bunch of disk I/O and load those data pages into the buffer pool. So that can be a fairly memory intensive operation requiring relatively modest levels of CPU. Now, the same database over time can evolve in its workload orientation to become more computationally intensive and perhaps require 16 cores, but much less memory than before. So the key point to emphasize here is that whatever combination of CPU and memory resources is required by the database, the service is able to respond and match, primarily because the scaling for CPU and memory is independent. And this is important both for providing good performance as well as trying to ensure that costs remain low. You can think of conceptually the memory to vCore ratio in serverless as being dynamically adaptive based on usage, and ranges all the way up to 24 gigabytes per core. In terms of scale-up latency, suppose for a moment that at one point in time, the database is using 2 cores, and then in the next very moment needs to burst to 16 cores. In this case, that scaling operation will generally complete in less than 1 second. There can be occasions where that scale up takes a few minutes to complete, but only if load balancing needs to be performed internally by the service. But that happens very rarely. Most of the time, this scale up speed is very fast, sub-second. So how does scaling in serverless compare to scaling in the provision compute tier? It's a very different world. In provision compute, the burden shifts to the customer to identify up front the amount of compute that's appropriate for the workload. Now, let's suppose I figured out that my database needs 2 cores. Then on generation 5 hardware, that database will be provisioned 10 gigabytes of memory. One of the benefits of provision compute is that those 2 cores and 10 gigs of memory are continuously allocated throughout the life cycle of the database, independent of its usage, so that you can think of provision compute as providing pristine performance dial tone. There is no reclaiming and reallocation of resources under the hood, as there is in serverless. The flip side is that those 2 cores and 10 gigs in provision compute are being billed whether or not they're actually being used. Now, suppose at a later point in time, the same database hits a bottleneck. So here again, the burden shifts to the customer to first identify that a bottleneck has occurred, identify what resource is causing the bottleneck, and then finally make a decision as to what amount of compute to actually scale to. That scale-up latency in provision compute always takes at least a few minutes. At the completion of that scaling operation, memory is reset, so representing some performance impact, and connections are always dropped, albeit rather briefly, but still representing a brief disruption in availability. Now, this can happen in serverless as well, but only when load balancing is required. Otherwise, most of the time, the scaling up or down in serverless is completely transparent to the customer, both in terms of the performance and availability impact. So with that, I'd next like to demonstrate auto scaling. So here I have an SSMS client with a database called DB1 that's already created. And if I select its service objective, what I see that it's in the hyperscale tier. S stands for serverless. It's on generation 5 hardware, and it has max vCores configured of 8. So this is a serverless hyperscale database that can scale up to 8 cores. What I'd like to do next is run 2 very expensive queries against this database concurrently. And if I want to make an observation about how quickly this serverless database is responding to that sudden surge in workload demand, I can look at the DMV called DB Resource Stats, which is reporting on various measures of resource utilization, including CPU usage over time. So here I see that I launched my workload at roughly 41 minutes and 45 seconds. and that by 41 minutes and 57 seconds, so about less than 15 seconds later, this database was consuming almost 100% of all 8 cores. So scaling from essentially 0 usage up to almost all 8 cores in less than 15 seconds. Now, as I said before, this scaling to 8 cores probably occurred in less than 1 second, and we're just limited here by the fact that I've launched this workload from my desktop remotely against the data center, but also we're limited by the resolution of the telemetry for this DMV, which is collecting and reporting on usage statistics once every 15 seconds. It's useful to understand memory management serverless, not just for performance reasons, but also because memory is billed in addition to CPU. So in SQL, there are various kinds of cache. The more prominent caches are listed here. You can think of buffer pool and column store as the in-memory caches that hold data pages. The query plan cache is also a large consumer of memory and is where precompiled plans reside that facilitate faster query execution speed. But then outside of cache memory, the another source of significant memory consumption are query grants. So each time a query is run, a query grant, memory grant is allocated, and then when that query completes, that query grant memory is deallocated. So in a sense, query grants already naturally align with the serverless paradigm of resource allocation based on usage. Cache in SQL historically doesn't work like that. So in the provision compute tier, once cache becomes allocated, it tends to remain allocated indefinitely. And this has, of course, performance benefits because when even after, say, a lower idle usage period, when that workload activity returns, because that data is already resident in cache, that query will execute all the more quickly. But that presents a problem for serverless in the sense that it can lead to unnecessarily high costs because memory remains allocated even though, or even in cases where usage is relatively low. So in serverless, we reclaim memory during lower idle usage periods and try to do this in a way that is sensitive both to the performance impact as well as price savings. So how does memory cache reclamation actually work in serverless? Each cache entry has a timestamp and is identified as hot or cold based on when that cache entry was last accessed. And every several minutes, we'll assess the total number of hot cache entries along with their size, compute that total hot cache size, look at that in relation to the total size of the cache, including the cold cache. And if that ratio, if that active cache utilization is below threshold, so representing some decrease in the amount of useful memory that's allocated, we'll then begin to initiate a series of resource reclamation steps. So how is cache actually reclaimed once we trigger that? It's not necessarily the case that the oldest cache entry is reclaimed first. So for example, if there's a buffer pool page that was, say, last accessed 5 minutes ago, but a plan cache entry that was last accessed an hour ago, then it could very well be the case that that buffer pool page is evicted first. And the reason for this is because the eviction of that buffer pool page is less costly in terms of performance to rehydrate that buffer pool page by fetching it back from disk. Whereas the regeneration of that plan cache entry, the recompile, can be much more expensive. So, this is illustrating how serverless is attempting to strike the right trade-offs, the right balance between reclaiming memory in order to reduce costs, while at the same time being sensitive in terms of how that's done to minimize that performance impact. Now, everything we just discussed about memory management serverless is equally true both in the general purpose tier as well as hyperscale. But again, unique to hyperscale is its layered caching hierarchy. And one of its first caches is the RPBX disk cache, which is as the name suggests, an extension of the buffer pool up to 3 times the size of the in-memory buffer pool. And the location of this RPBX cache on disk is on the same machine as where that compute is running. So a cache miss in memory that becomes satisfied by RPBX is very performant. Now you'll see that each replica instance has a serverless resource manager running inside of it that's responsible for the allocation and deallocation of both memory cache as well as RPBX disk cache. And a key point to emphasize here is that because this resource manager is running on each replica instance, it's tuning the amount of resources that it provides and takes away in response to the specific workload demand on that particular instance. So for example, because the primary replica handles both read and write operations, it may have much more aggressive scaling requirements than, say, an HAR named replica. And this serverless resource manager will precisely tune the amount of resources delivered, even though the workload demand across those replica instances can be quite different. So how exactly does RPBX cache management work in serverless? You can think of that cache as being divided into zones, where each zone contains enough AK pages such that the zone size is on the order of 1 gigabyte. And what we do is we identify the hotness or coldness of each page in each zone, and then compute a score for the zone based on its total number of hot pages. And then conceptually order those zones from the highest score or the highest zones with the highest number of hot pages to the lowest score or the zones with the lowest number of hot pages. And we'll reclaim the coldest zones first. We'll trim the disk for this RPBX cache of those coldest zones first. Again, what this is an example of is how we're trying to be sensitive to the performance impact from these kinds of resource reclamation activities. So pausing and resuming, how does this work, let's say in the general purpose tier? So serverless is constantly analyzing all kinds of different usage history. And if the number of sessions and the CPU usage for the database are 0 over a length of time that was provided by the auto pause delay, which is this parameter that's configurable by the customer, then the service will take the liberty to pause the database. And so what this involves is first taking a tail log backup to ensure an orderly shutdown of that database, then detaching the database files, and then finally terminating the underlying SQL instance, at which point billing for compute is stopped. The length of time to pause a database, which is important for cost-related reasons, typically is in a range of 1 to 10 minutes, and most often takes around a minute, and is largely due to taking that tail log backup to ensure an orderly shutdown. Now, at a later point in time, when activity returns, say in the form of a login, the service is listening for that, of course, and when it detects the login has occurred, starts billing for compute, launches the SQL instance, and as part of that SQL initialization, attaches the database files. And at the completion of that workflow, the database is then online and able to process requests. The latency to resume a database is typically about a minute. It can take as little as 30 seconds, but of course that resume time is, unlike, say, the pausing time, is very important for both performance and availability related reasons. So now that we have a little bit of understanding about what serverless is and how it works, it's useful to overlay that understanding on top of the architecture and connect that back to the customer performance experience. So serverless is a 3-tiered architecture. It has a control plane, which contains the gateway service responsible for connectivity, the management service that's responsible for DDL operations like create and drop. Sitting below the control plane is the data plane, where there are tenant rings, which are collections of virtual machines that provide the compute to power the databases in SQLDB. And then below the data plane is the storage plane, which contains the remotely stored database files. So let's follow the lifecycle journey of a database that starts in the pause state and follow that lifecycle, overlay that on top of this architecture. So the client first attempts to connect to the database. That connection request is received by the gateway service, which will reject that first connection attempt because the database is paused. So it's very important in serverless, especially if you're using pausing and resuming, to ensure that the application has connection retry logic wired in. Then on a subsequent connection attempt, the gateway will authenticate, pass control over to the management service that then works in cooperation with the service fabric to identify a tenant ring and then a machine within the tenant ring that has sufficient capacity to handle the scaling operations for that serverless database. Once that machine has been identified, a SQL instance is launched, and as part of that initialization process, these remotely stored database files are attached, as we just discussed, and at the completion of that initialization process, that database is online. Now, on this machine hosting the SQL instances with different serverless databases is RG Manager, which is among its duties performing constant surveillance of utilization of the machine itself, as well as utilization of each of the individual databases that it's hosting. And if it detects a bottleneck, it attempts to resolve it. So for example, if there are two serverless databases sharing the same subset of cores on the machine, and those cores become too hot, they're overloaded, then that condition gets detected by RG Manager. It will attempt to identify a cooler set of cores on the same machine that it can reaffinitize one of those serverless databases to in order to relieve the bottleneck. That reaffinitization operation is very quick. It's a kernel level call completing in on the time scale of microseconds. Now, it could be the case that the machine itself is overloaded. There are no cooler cores to be found. Under those conditions, the service fabric re-enters the picture, will identify a different machine in the ring with sufficient capacity to handle that scaling operation, and then orchestrate the repositioning of one of those serverless databases from the hot machine to the cooler machine. And that load balancing motion can take up to a few minutes to complete. So that's what I referred to earlier. That can occur in serverless, but as I mentioned, it's a much more rare occurrence. Most of the time, all of the scaling operations for a serverless database can be satisfied within the context of the same machine boundary. And so the impact to either performance or availability while that rescaling is occurring is virtually imperceptible to the customer. So now let's discuss how pricing works in serverless. And sticking with the hyperscale examples, I'd like to draw your attention to the orange bars in this chart. So to think about how pricing in serverless works, it's often useful to compare it against provision compute. So in the provision compute tier for hyperscale, the cost for one core for 1 hour, depending on the region, of course, is around 29 cents. Whereas in the case of serverless, the cost for one core for 1 hour is 59 cents. But that's only true in serverless if the database is using that whole core for the full hour. But if the average usage over time, over that 1 hour, is less than a core, so even if the database is still peaking up to 1 core, but its average usage over time is less than 1 core, then because serverless charges for the amount of compute used, the price is less than 59 cents. And so if instead the average usage over time were, say, a half core over the full hour, then the cost would be half of 59 cents, which puts it into a ballpark of the cost for provision compute for 1 core. In other words, if the average usage, both in terms of memory and CPU for this serverless database, is less than 48% over time, then serverless tends to be a better pricing fit. Whereas conversely, if that usage over time tends to be greater than 50%, then provision compute tends to be the better pricing fit. So how is the compute bill actually calculated? Essentially, we're billing for the larger between CPU and memory used each second. That naturally leads to the question, well, how do you compare CPU usage to memory usage when in fact CPU and memory are different resources with different units? So for billing purposes alone, we rescale the amount of memory that's used each second by 3 gigabytes per core. And once that rescaling has occurred, just for the billing calculation, we'll be able to compare whether or not memory, as expressed in terms of vcores, is larger or smaller than the number of vcores used for CPU. So, for example, if over 1 second 1 vcore of CPU is used, but let's say 6 gigabytes of memory is used, then we'll rescale 6 gigs of memory by 3 gigs per core to come up with 2 vcores of memory that's used, and then compare that against 1 vcore of CPU that's used. And because memory is the more dominant resource in that calculation, that's what's billed for that 1 second in time. And then at the very next second, let's say the CPU usage increases suddenly from 1 to 8 cores, but the memory consumption hasn't changed much. Then because CPU is the dominant resource for the next second, it's CPU that's billed. And so to compute or to calculate the compute bill over any given interval of time just amounts to determining the number of vcore seconds or vcores that are used each second, adding that up to come up with the total number of vcore seconds for that time interval, and then multiplying that quantity by the cost per vcore to come up with the amount of compute that's actually billed, to which the cost for storage is added, and together those combine to determine the total cost for the database. In the case of hyperscale, this billing algorithm is applied independently to each of the replica instances for the same database. So with that, I'd like next to demonstrate compute billing. So here again, I'm showing the Azure portal, the same server LS2, but in this case, a different database called SHS1. And you can see this database is configured with serverless in the hyperscale tier with a max vcore of 16. And then you can see on the chart below that's its compute usage over the last hour has about 2 bursting usage periods, each of which correspond to increases in the amount of compute that's billed. Now, if I'd like to estimate the compute costs, let's say over a 24-hour period, then as we were saying earlier, we just need to add up the total number of vcore seconds over that interval of time. And that's given by this metric in the lower left-hand corner of this chart. So roughly 281,000 vcore seconds is the billable quantity for the last 24 hours. So 281,670 vcore seconds to be precise were billed over the last 24 hours. And if I know the compute unit price expressed as dollars per vcore second, which is fractions of a penny, I just take the product of those two quantities to come up with the estimated compute cost of $46. Now, if we compare that against the cost for the same database with the same workload in the provision compute tier with 16 vcores configured, then the cost there comes to $111. So in serverless, with this particular workload pattern, the price savings relative to provision compute is around 50%. So in terms of roadmap for serverless, we've been discussing the recently introduced support for automatic compute scaling and hyperscale. We're working on adding support for automatically pausing and resuming in hyperscale as well. We'd also like to add support for elastic pools. So a pool that contains, say, tens or hundreds of databases may have workload patterns for each of those databases that are fairly well correlated over time, so that if you looked at the usage pattern of the whole pool containing all those databases, you very well might still see peaks and valleys. And rather than sort of shift this rescaling burden of elastic pools to customers, we'd like to automate all that in the form of serverless elastic pools. We're working on raising the compute limits for serverless beyond 40 cores. We'd also like to offer automatic scale out in hyperscale for a read-only workload. We're working on improvements in pausing and resuming. For example, we'd like to reduce the auto pause delay, which again is this period of time that the database needs to remain idle before it will be paused, and reduce that minimum time from 1 hour, which it is currently, to as low as a few minutes. And that will give databases more opportunities to pass through, more pause and resume cycles and enjoy even greater price optimization. We are continuing to provide built-in connection retry logic into various SQL client libraries. So right now, all of the SQL client drivers that are part of .NET libraries have built-in connection retry logic already, and we're looking to extend that support to other client drivers as well, which is, again, important to have this capability, especially in serverless for databases that pause and resume. And then finally, we'd like to provide price and performance insights for customers seeking to take advantage of serverless, either by analyzing their on-premise database or an existing provisioned compute database, and assess ahead of time what the price and performance picture would look like were that database to move into serverless. So in summary, Azure SQL Database is price and performance optimized for single database workloads with intermittent and unpredictable usage. It automatically scales compute and at the discretion of the customer can be configured to automatically pause and resume, and then bill just for the amount of compute used per second based on the workload demand of the application. So for more information, I'd invite you to visit aka.ms/SQLDB serverless. Thank you.